Well, hello again. Welcome back to Statics Engineering 211. I'd like to pick up where we left off last time, and we had talked about the dot product. And the dot product we used to find the projection of one element or vector, I should say, onto another. And then the other thing that we talked about was we used it to help us find the angle between a couple of vectors, and when these vectors are possibly in 3D or 3 space, that becomes very useful because that angle can be hard to get at. So I wanted to reinforce some of this theory with some problems, so that's what we'll do today. So we'll start with this first example. We've got some sort of a pole here, pole or a spar of some sort, and it's maybe stuck in the ground at the origin at O, and goes up to point A where we've applied a force to this, and we're given that the force is minus 20 in the I direction, minus 50 in the J direction, or excuse me, plus 50 in the J direction, minus 10 in the K direction, so it's kind of back and to your right. We're given the location of A, and I don't know that we have any units on that, and that's okay. And what we'd like to do is find the magnitude of the projection of F on this pole OA. Okay, so let's see if we can do that. What we're going to need to do first is find what the position vector for OA is. So let me do that. ROA. What's that going to be? If we were to describe how to get from O to A, what would that look like? Well, giving someone walking instructions, it looks like we would probably go, what, 3 in the I direction, and then 2 in the minus Y direction, so I'll go minus 2 in the J, and then we'd have to go 6 in the K. Now if you wanted to, I mean, you could take this point as 0, 0, 0, and this point as 3, oops, yes, 3 minus 2, 6. Take the end points and subtract the beginning points. However you want to get there. A lot of times I just envision myself starting at this point and give myself instructions how to get to A, and that gives us our position vectors. So I can say then that the projection, which remember is going to return a scalar, so this is just going to be the magnitude of the projection, is equal to that force vector F dotted with the unit vector that represents OA. Okay, so I could say that this would be F dotted with the position vector for OA divided by the magnitude of that same position vector, right? So let's see if we can put this all together. We could say that this is F is just given to us as minus 20 in the I direction, plus 50J, minus 10K. So we've got that. And then we're going to dot that with this R that we found up here. Let's see, 3 in the I, minus 2J, plus 6K. And then I have to divide by the magnitude of that, which would be 3 squared plus a minus 2 squared plus 6 squared. Let me double check my work there. 3 minus 2 plus 6. 3 minus 2 plus. Yes, I think we're good. So when you go through and remember this is dotting, exaggerated that dot a little bit so we don't confuse it with multiplication. I think this denominator turns out to be 7, doesn't it? So maybe I'll go to a couple more steps here than I normally do, just so we know where some of these things come from. Minus 20 in the I, plus 50 in the J, minus 10 in the K. We're going to dot that with, what would that be, 3 sevenths in the I, minus 2 sevenths in the J, plus 6 sevenths in the K. So this would turn out to be equal to 3 times 20 minus 60 over 7 minus 100, because plus 50 and minus 2, minus 100 over 7, then minus 10 minus 60 over 7, which gives me what? Minus 220 over 7. Let's see. That's real close. I mean, if we had a calculator, you could calc it out, or you could say it's approximately what? Minus 10 pi. Is that right? It's 22/7 approximation for pi. So yeah. So we could say that the projection is equal to minus 31.4 pounds. Okay. Speaking of the units, this would have had pounds, and then this one, this item here, would have been whatever the distance are, distance over distance, right? So whether it's feet or meters, as long as they were consistent, as long as they were the same, we're good with that. Well, there's our answer. Why is it negative? Well, it's negative because our position vector is going from O to A, and F is going opposite it. Okay, so that's why we end up with a negative sign. But this can be an important answer, because that's what that's doing, is really trying to push that pole into the ground. If it was your task to design this footing here, this number would be a very important number. So 31.4, and that would be going from A to O. This is O to A. If you go from A to O, you would just take the positive of that, 31.4 pounds. So good use of the dot product and good practice. Let's move on to another problem, similar problem, but again, hopefully good practice. So let's take this problem. We've got a flagpole here, and maybe it's on the back of a ship or something, and we're told the height of the flagpole, not just to the bottom of the flag, but the height of the flagpole is 12 feet, and we've got some guy wire supporting the flagpole. I don't think you're normally supposed to do this per flag etiquette, but I think if it's at the back of a ship or something, then this is fairly standard. So we then, on our XY plane, come out 6 feet in the X direction and minus 4 feet in the Y direction, and we have this point here where we connect this guy wire to the top of the pole, and obviously that guy wire is going to have some force acting down it. We're told the magnitude of that force is 28 pounds. Incidentally, the flag here, I think I'm missing a few stripes. I used to always ask students in classes, how many stripes does the flag have? And of course, the answer was 13, and then I would ask, did it ever have more? And that was always a little harder for people. And there was a time period where they were going to add a star and a stripe for each state, and it got to 15. And I think they realized the flag was going to start to look funny, so they went back to the original 13 for the original 13 colonies, and then added the stars. I'm missing a star there. So the 50 stars now, of course, Hawaii and Alaska being the last two. So it's always interesting when you look at a 48-star flag. And there's a lot of them floating around there. 48-star flag has a square grid or a square matrix, and then if they're skewed, the columns don't have the same number of stars in them. You know, that's usually a 50-star flag. So there's your flag trivia for the day. Well, again, what we'd like to find is the projection of that force on that pole. You can imagine as that force pulls on that pole, it's going to try and push that pole down into the ground. So this is a good question to ask. Let's see if we can do this. The process that we're going to go through is going to look something like this. The projection is going to be equal to the force dotted with the unit vector for the pole. So let's see if we can come up with these pieces. What's F going to be in this case? Well, I have to take the position vector from B to C. So F is going to be equal to the magnitude of F times the position vector from B to C. So I'm going to take the position vector from B to C and divide by the magnitude of that position vector. So we know that this is 28 pounds, and then I'm multiplying by, how do you get from, we're going from B to C. Yeah, okay, I haven't got the unit vector. The unit vector of the pole is going to be straight down. I'm sorry, that's the unit vector for the pole. Here is the unit vector for the guy. So this is essentially RBC. Okay. The unit vector for the pole is pretty easy, isn't it? And I can put that down here. This is the unit vector for the pole. I got a little bit ahead of myself putting vectors on there. And it's going to be what? 0 in the I plus 0 in the j plus 12 in the k. Okay. And then I divide this by the square root of 12 squared, which is equal to 1 in the k direction. Okay. And which way is that unit vector pointing? The way I have done it, 12 in the k, that unit vector really points up. So I probably shouldn't have put this arrow in here at all. Fix things up here. So our unit vector for our pole is pointing up, which is fine. That'll have some bearing on the final answer, and we will talk about that. So that's the unit vector for the pole, and it's pointing up. Okay. So we've got that done. Let me run back over here and work on this. So then B to C. Imagine yourself at the top of the flagpole. I used to have people that sat on top of flagpoles. I don't know why, but imagine yourself at B and give yourself instructions to get to C. I mean, if you wanted to, you could define coordinates at B and define coordinates at C and take those C coordinates and subtract the B coordinates. But I think it's probably easier just to imagine how to get from B to C. And what does that look like? Looks like you're going to have to go 6 in the I direction, and then minus 4 in the j direction, and then minus 12 in the k direction. Does that work? Sometimes doing it not in order is useful. Minus 12 gets me to there, back to the origin. Then minus 4 in the y gets me to there, and then 6 in the x gets me to there. So that's true. So this would be, of course, feet, and we would divide then by the square root of 6 squared plus 4 squared plus 12 squared. The negatives go away, of course, when you square it. And that would be feet also, so those would cancel and we'd get units of pounds, which hopefully makes sense. So when you go through this, go through the math on this, I think this turns out to be, what, 14? Yeah, 14. So you're going to have 2, so you multiply that by 2, that turns out to be 12 in the I, minus 8 in the j, minus 24 in the k. Okay. And that would be pounds. So if we were looking for F in Cartesian form, there's your answer right there. We use the position vector to get that. Well, I'm not necessarily asking for that. I'm asking for the projection of it down the pole. So what I'm going to do is say that that's equal to F, which is this thing, dotted with the unit vector for the pole, which is to say that I have 12 in the I, minus 8 in the j, minus 24 in the k, and I'm going to dot that with what? 1 in the k. So when you do that, you simply end up with what? Minus 24, minus 24 pounds. Now again, why the negative sign? Because we've taken the unit vector, fairly arbitrarily, took the unit vector going up the pole. Had I taken the unit vector going down the pole, it would have been a positive number. So this means essentially opposite of the unit vector for the pole. So we know it really is pushing down into the ground. That becomes important. I had a problem one time. My brother does a lot of HVAC work, and they were adding to a chimney. So they had a chimney on a school. Apparently they didn't want all the kids to pass out on the playground. So they were adding this steel flue to the top of this chimney, and they were going to put a guy on it and some guy wires. And we had to figure out these guy wires, what kind of forces that would put on the existing brick chimney. So I helped him with that. So very similar problem, a little more complicated because you're dealing with 3 guy wires at once, but you're going to go through a similar process. So with this we found, and some of these other numbers might be important too in terms of the force in the guy wire, but for our purpose we just wanted to find the projection on the pole, which would be 24 pounds down. Okay, that's what that is really saying, 24 pounds down. That's not a very good pound, is it? There we go, 24 pounds. I think I started out with this problem thinking about doing it in metric, but I figured with the US flag we better do it in standard units. So 24 pounds down. Okay, well I've got one more problem. Remember that the dot product not only helps us find the projection, but it also helps us find the angle. So if I have a couple of vectors in space, I can use it to help me find the angle. So let's see what we've got here. I've got again a pole that's going straight up the z-axis, a lot like that flagpole. This one is in the metric system, so it's 4 meters, so that's going to be what, about a little over 12 feet, so it could be just the flagpole without the flag on it. And we've got a guy wire that goes from the top at A down to C that's located on the x-axis and is 3 meters out on the x-axis. And then we've got this other guy wire that goes from A to this point B out here that's 2 meters in the x and 4 meters in the y and is in the xy plane. Both of these points here, C and B, on the xy plane. And we're not interested in necessarily forces on this problem. What we're interested in is the angle in 3D between these two guy wires. There's some angle in space between those guy wires. So what I'd like to do then is come up with that. And I recognize that if I've come up with a position vector for, let's say, B, and I were to dot it with the position vector for C, so what do those look like? There's the position vector for B, and here is the position vector for C. In dotting those together, I could say that that's equal to the magnitude of that position vector for B times the magnitude of the position vector for C times the cosine of theta. And I could rearrange this as we did last lecture and recognize that theta is going to be the inverse cosine or the arc cosine of RB dotted with RC, those are vectors, divided by their magnitudes. Okay, and this is all in the argument here. Okay, so if I can find RB and dot it with RC and then divide by the product of their magnitudes, I'm off and running. So it looks like it's really a task of finding RB and RC. So let's see if we can do that. Maybe I'll put those over here. What's RB going to look like? Well, again, you could find the coordinates of B and the coordinates of A and subtract the coordinates of B from A. Subtract the coordinates of A from B, take the end position and subtract the beginning position. I think it's probably a little bit easier just to imagine yourself again at A, sitting on top of that post, probably wanting to get off of it. And how do you give yourself instructions to get to B? I think those would look like something like this. 2 in the I direction, plus 4 in the J direction, minus 4 in the K direction. Does that make sense? Sometimes if you go in a different order, it helps. So the Z would be minus 4, so that works. Then the Y would be 4 positive, that works, that gets you to there. And then you have to go 2. Okay, so we go down, over, and back like that. So then RC, and again you could take your C coordinates and subtract your A coordinates. Probably again easier just to think of going from A to C. That's going to be what? 3 in the I direction plus 0 in the J minus 4 in the K. Again, you got to go down this minus 4. That puts you right there. You don't go any in the Y, so that's why we have 0 in the J. And you just go out 3 in the X. Now, if I want the magnitude of that, the magnitude of B is really just going to be the square root of what? 2 squared plus 4 squared plus 4 squared. Again, negative sign goes away when we square it. Comes up with the square root of what? 36, which is 6. And C, the magnitude would be the square root of what? 3 squared plus 0 squared plus 4 squared. And I've been very sloppy in my work there. I didn't square the 0, and I recognize the negative went away when I square it. And that turns out to be what? Square root of 25 or 5. Okay, so now I've got the ingredients here. This is my equation or my recipe, and I've got the ingredients that I can put into it. So I could say then that theta is going to be the inverse cosine of these two vectors, RB, so 2 in the I plus 4 in the J minus 4 in the K, and we're going to dot that with 3 in the I plus 0 in the J minus 4 in the K, and divide by multiplying these together. B is 6, and times, I'm going to be careful, I don't want to put a dot for multiply, so I'll say 6 times 5. Okay, so this turns out to be equal to the inverse cosine. What do I have? I'm going to have 2 times 3 is 6, plus 4 times 0 is 0, plus minus 4 times minus 4 gives me what? Minus 4 times minus 4 gives me 16, positive 16. So I'm going to then divide this by 6 times 5, which is what? The arc cosine of 22 over 30. Is that right? Let me make sure that evaluates out right. Yeah, 42.8, that's what I got. So theta is equal to 42.8 degrees. 42.8 degrees, so I'll double check that. That is, yep. Okay, so we did the dot product, we divided by the product of the magnitudes, took the inverse cosine, we've got that. So that would be our answer. One thing probably worth talking about is we could, if we wanted to, say that this was also equal to the arc cosine of what? RB divided by its magnitude is really the unit vector for B dotted with the unit vector for C, right? So you could, if you wanted to, you could come up with this unit vector for B. You could take that and that. So the unit vector for B is just going to be 2 in the I plus 4 in the J minus 4 in the K divided by 6. Okay, and if you look at essentially the way that you can do the your operations with the dot product, this is really just a restatement of the rules of the dot product. So that sometimes that saves you a little time because you may know the unit vector and you don't have to go through that, but not a big deal to get hung up on. Well, that's how to use the dot product to find the projection of one force onto another axis or another direction, and also how to use the dot product to find an angle in space. This might be a fairly difficult angle to find with those lines in space. So wanted to go through those problems and practice that. When we get together next time with the next lecture, and this lecture was a little short because I'd prepared the problems already. Normally it takes a little longer because I'm writing these out on the board or whatnot, but I didn't figure that you needed to see me write those out. But we're going to spend more time when we get together next time, go into the next subject, which is moments. What happens when we have a force acting at some distance from a point or an axis. So that's going to be a good subject and a new subject, and that's what we'll do next time. Again, thank you for watching, and take care till then.